All right. I will begin with a word of prayer. So, dearly Father, we thank you for this day. Again, I thank you for this class, these students. Just ask you to help us to use this time wisely, that we make the most of the time we have left. Lord, in your name I pray, Lord Jesus. Amen. So I wanted to talk to you guys just a bit today about geometry and surfaces, because I said I would, so I better do that. So I'll try to be brief. And so some of you are in modern geometry right now, so this might make more sense to you perhaps. But I want to tell you a little bit about the geometry of surfaces from a sort of more, equations-based perspective. All right, so you guys are in modern geometry. You've done all kinds of stuff with axiomatics, right? But let me just explain to you, like, what is a geometric surface? What's a geometric surface? A geometric surface is a two-dimensional space paired with a so-called metric. So a metric is something that allows you to measure the distance between points. And typically the metric is described sort of infinitesimally. All right, so probably the best thing for me to do is give you some examples of this. Like example 1, you can let M be like the plane, all right? And the metric, we typically use a G for the metric in this context. And let me kind of explain what that is. So here, G, if you'll allow me this kind of quaint 19th century characterization of these things. Now, if you do so choose to come take manifolds with me next semester, we'll make this like more formal and precise, but this is essentially it. I mean, the metric, the Euclidean metrics, is dx squared plus dy squared. So how do you calculate the length of a path? So like the length of a path gamma is, like the integral of the square root of like dx dt squared plus dy dt squared dt integrated from, say, t1 to t2, right? Or let's just kind of be more, I'd rather write that for the sake of, getting further in a shorter time. We're really just integrating this over the curve, all right? That's the Euclidean length of the curve. This is the arc length formula, right? So a two-dimensional space, what that essentially means is that there's a one-to-one smooth correspondence between the set and the plane, at least locally. So of course the plane is a surface, and this is Euclidean geometry. All right, so the plane paired with this metric defines Euclidean geometry. From this, you can build all of the concepts that you like. Okay, so, but there's some weird stuff you could do. Like, you could take M to be, let's say, like x comma y, such that y is greater than 0. This is like the upper half plane, all right? And in this, you could use the metric. You could let g equal to like 1 over y squared, dx squared plus dy squared. So like the length of a path would be, you integrate over the path the square root of dx squared plus dy squared divided by y, because I can pull it outside the square root. Now that's weird, right? That's not Euclidean geometry, but that nevertheless defines a geometry. Like I can calculate the distance between points, all right? And so for every geometry, you can understand the geometry more completely if you understand what are called the geodesics of the geometry. So like geodesic is path of shortest length. So like if you give me a pair of points in the plane, what's the geodesic between the points? You guys should have known this in like 4th grade, right? You just connect the dots, right? The line is the geodesic. What's the line, what's the curve of, what's the geodesics for example 2? A line? Maybe. So like, yeah, if my 2 points are like this, you're right. There is a geodesic, a vertical line segment. That is in fact the geodesic between those 2 points. However, if my 2 points are not vertically situated like that, the shortest distance between that actually follows, it's the length along a path which is a half circle, which vertically tangents to the I don't even know how to say it. It's like this. I never got probably able to do. I'm going to try, guys. I'm going to try. So like that. There's two kinds of geodesics in this geometry. There's either vertical line segments or there's half circles that that terminate on the x-axis here. Yeah.
Is that a half circle?
Yeah, I'm trying to draw a half circle, but it's, you know, I tried.
Why is it the path between the 2 points?
Well, yeah, I mean, I'm saying that the distance from this point to that point, that distance.
But it's formed from that.
I'm saying the curve of shortest distance between those 2 points happens to be a half circle if we measure distance according to this weird notion of distance. Let me try to explain this more. What this is saying is you're using like a little ruler to measure distance, but the closer you get to the x-axis, the more stretched out it gets. You see, as y goes to 0, that goes to infinity. So actually, to actually get to the x-axis from this point, there's infinite distance from here to here. You can never actually reach the x-axis. Like that's how that works. So if I pick, so here's and so in this geometry, that circle would be a line because we think of the geodesics as being the lines of the geometry. So a line becomes defined as the path of shortest distance between 2 points. All right? And anyway, so if we take, you know, this red line and I take a point not on the line, like let's say this one over here, I'm trying to, yeah, like this point right here. How many lines go through that point that's not on the red line? So, I mean, there's going to be like that one, right? But there's also this one. If I did this better, rats. I'm sorry, I'm not saying this right. You guys are in the geometry class. You guys tell me, what is the replacement for the parallel postulate in hyperbolic geometry? This is, by the way, a hyperbolic geometry.
Is that there are more than one parallel to a given line through a point not on that given line?
More than one line.
Given line
more than one parallel line, right?
Yes.
Through P, not on, you know, parallel to this L. So I'm saying like this is L. And so what lines are parallel? I'm sorry, guys. I had this all thought out like a week ago, and then a week happened, and my ideas have gotten a little bit displaced. But in fact, you can see that there are more than one. see if I can find a better. Goodness gracious. There's a simple picture to draw here, and I just can't think of it. It's killing me. Gah. Well, oh, by the way, so you might wonder, what is the actual distance between 2 points? Here's a formula for it. The distance from, say, P1 to P2 is like 2 times the inverse sine of the Euclidean distance from P2 to P1 divided by 2 times the square root of y1, y2. So I don't know how, I mean, and there's like 3 other formulas that I found on this is from the Wikipedia article for the Poincare half-plane model. That's what this is. Poincare half-plane model. So if I could, the thing I'm forgetting about is, what's the parallel postulate say exactly? It says that there's just one parallel line to
For every line L, or for a given line L and point P not on L, there exists one line, only one line through point P parallel to L.
Right. So the thing that's, the thing that's missing here is what characterizes parallel lines, right? Because just because I show there's 2 lines through the point off the thing doesn't show that they're parallel lines, right?
Parallel means they never touch.
No.
In art class.
We can't say that they're if
You can't say that they never touch, though.
They're parallel.
Well, you just told me that there's 2 lines. You just told me there's 2 parallel lines. You said you have a line, you have a point off the line, and then you have 2 parallel lines that go through the point.
Yeah, but they don't. But they're parallel to the line. They're parallel to this line. They're not parallel to each other. Only in
Okay. Oh, so you're saying they're parallel to. Okay, I got you. So all right. I think I understand now.
can't characterize parallel lines.
So I need to like to illustrate this. Here's my here's my line, right? Here's my point, not on the line, right? Let's say here, I don't know, whatever. And then I need to do what to show it's a hyperbolic geometry? I need to show that there are more than one what?
Line through the point.
lines through that point that aren't.
That what?
That never touch. See?
That never touch the given line, the black line?
That never touch the given line.
All right, so like this one would be 1, right? But of course, you could also do this one, and this one, and this one. In fact, there are infinitely many. There, thank you. That's what I mean. If I've been teaching modern geometry this semester, it would have turned out better. Oh well. So my point to you guys is just that you have Euclidean geometry, this is an example of hyperbolic geometry. The difference, though, here between this and so you guys are using these formulas?
No, sir.
No, you have not, right? You have axioms. Yeah? But you can derive through calculus that the shortest path between 2 points, variational calculus, the shortest path between 2 points is in fact either a vertical line segment if the points are vertically situated, or it is a half circle terminating on the x-axis if they're not vertically situated like that. You can derive that. Those are your lines. And then you can sort through all the other axioms that you guys have talked about, and those axioms will be met, they'll be realized by this concrete set and metric and notion of distance. All right? And so this is one of Poincare's 2 models. Poincare also had his disk model. The Poincare disk model is, I got to look it up here, just give me a second. So in the Poincare disk model, it's probably easiest to describe like this. It's M, Z, and let's say in the complex plane, think of it as R2, right? Such that the modulus of Z is less than 1. So that's the set. What's the metric? Well, the metric in complex notation looks like this. ds is 2 times Euclidean length of dz divided by 1 minus the modulus of z squared. Now, if I write that in terms of like Cartesian stuff, this is exactly, you know, like, oh goodness gracious, 2 times the square root of dx squared plus dy squared divided by 1 minus x squared minus y squared. All right. Well, hey, back on the board. I know it's for a good cause, but come on. Anyway, so this is called the Poincare disk model, and so it's like the open unit disk, and this is the definition of the metric that's given for that. Do you guys see how this works? So if I like draw a picture of it, right? How does that work? If you look at where does that become infinite? So like if I take a point here, and a point here, and a point here, and a point, what the distance between these points becomes larger as you go towards the edge, right? Because this goes to infinity. So if you're calculating the distance, between 2 points with respect to that metric, it becomes infinite at the edge. So in this thing, the edge of the disk plays the role that the real axis did in the Poincare half plane model. And I don't know right offhand like what the geodesics look like at that. I think they're things that are like this. It's the thing I'm looking at says that this is called an ideal triangle. An ideal triangle is one with 0 angles. You have a triangle with a 0 angle at a vertex. That's weird. But that's how it is. See, because these two lines, they're coming in. They don't actually reach, this is a point. Like the vertex and the triangle is not actually in the space. In that sense, it's an ideal triangle.
A triangle?
Yeah, well, there's triangles in here if you use your imagination. Pick a point in here. Oh, man. Fine. There, I add that. Now you can see the triangle, okay? There you go. There's your triangle. Obviously a triangle, right? Okay, so listen, what is a triangle in another geometry? It is defined by 3 line segments and 3 points, or perhaps an ideal point in this case. So like you can define triangles in other geometries the same way you define them in Euclidean geometry. And this is an ideal triangle in the sense that you actually have 0 angle on that vertex. The way that works is you've got 2 parallel lines. They never cross, and their limit point is that ideal point. So they're parallel, and it takes infinite distance to get from, to the edge, according to that. Anyway, this is an ideal triangle. It's a triangle of maximum area in this hyperbolic space. So let me tell you a little bit about the history of all this. So essentially, Gauss was playing around with this kind of stuff in the turn of the century. He had some like personal notes that he published. He hadn't published them. He distributed them to friends and family or whatever, but he didn't publish this stuff. And the reason he didn't publish this stuff, people speculate, is because of what philosophers said back in the day. So like here's what Kant in his Critique of Pure Reason said about the necessity of Euclidean geometry. He said that space and time are not discovered by humans as objective features of the world, but are part of an unavoidable systematic framework for organizing our experiences. This was sort of a translation of Critique of Pure Reason. And so it said that Gauss did not publish anything about hyperbolic geometry out of fear of the quote-unquote uproar of the Boetians, which is probably politically incorrect. if you were to properly translate it. Anyway, which would ruin his status as the sort of prince of mathematicians of the time. So he was cowardly and did not publish his non-Euclidean geometry. And what happened was about in the 1830s or so, Bolyai and Lobachevsky both found axiomatic hyperbolic geometry. Now, if you read the history of this stuff, they'll give credit to people back in the 12th century, like Sakkari and other dudes, and there's Arab people in with good grief, India, Arabic. What's wrong with me? I mean, there's some mathematicians in like the Middle East, not the Middle East, maybe Egypt. Goodness gracious. No, older than that. Oh man, the words are escaping me. But the point is that there was progress outside of Europe on these things, in India and also in the Middle East-ish countries. But it was always for the purpose of trying to prove the inescapability of the parallel postulate of geometry, right? The parallel postulate is a logical consequence of the other things, right? So I think it's kind of unfair to say that those people were working on hyperbolic geometry, because what they were just trying to do was to prove that the parallel postulate was a necessity of the other ones. So were they really working on hyperbolic geometry? I don't know. I think it's kind of seeing the past with overly rosy colored glasses or something. I don't know. I think really properly hyperbolic geometry was born in the 19th century in the work of people like Gauss and Bolyai and Lobachevsky. Anyway, so the point, this came a little bit later. Poincare was like a little bit later in the 19th century. The Poincare disk model and the half-plane model of hyperbolic geometry, these are concrete. You can do calculus on these things. There's formulas for distance between points, right? It's not synthetic, abstract like your course, right? This is analytic geometry with souped up different notions of distance. This is sort of the soil on which like modern manifold theory and the rest of this stuff has been born from. Riemann gave this, incredible lecture in like 1859, basically seeing the view forward for talking about abstract n-dimensional space and how to study geometry on it, basically abstracting these ideas to much more general spaces, which is what that course I'm teaching in the next semester is about, roughly speaking. Not that we're doing this stuff so much. I mean, maybe Homer problem or something, but just one more thing, and I'll stop for this stuff. But the interesting thing is Gauss proved, among other things, he proved this formula. He proved that the integral over a triangle of the curvature is equal to alpha plus beta plus gamma minus pi. So and now of course that begs the question, well, what on earth is the curvature, right? So the curvature, there are different ways of defining it, but just because I don't want to teach it to the course in like the last 10 minutes of this class, you can derive a formula which is h squared times the Laplacian of the log of h. H squared times the Laplacian of the log of h. This is the curvature. So this is for if your metric g is basically, let's say if it acts on VW, it's something like 1 over h squared times the dot product of v and w. In other words, let me just be more concrete. H squared for my examples. All right, so like h squared, for example 1. For example 1, my h squared was what? I mean, h is what? For example 2, what's h? For example 3, what's h? So maybe you're not seeing past my notation. Like this, admittedly, is bad. Instead of writing, good grief. The notation's getting me. It's 1 over h squared times dx squared plus dy squared. There we go. Now you should be able to see it. All right. So if you look back, for example 1, h is equal to 1. All right, h is just 1. For example 2, h is y. For example 3, h is, let's see here, notice that g, we could also call g as ds squared, guys. So that's notation it's a little bit antiquated. I mean, this is the notation people were using around the dawn of World War I. Something like that. It's not wrong notation, just unfamiliar to us. Let's see here. So that would be, goodness gracious, I'm trying to think. If I square this, what do I get? I get 1 minus 1 minus 1 minus x squared minus y squared divided by 2, maybe? Is that right? Because when I square it, I should get h squared. So if it's unsquared, that means the thing that's sitting here is h, I think. All right? And then there's one other example I should tell you guys, and then I'll really try to draw my thoughts together and stop this part of the course, which is, so you have Euclidean geometry, which of course we're most familiar with. You have hyperbolic geometry, which I just shared with you there. But there are also what are called spherical or elliptical geometries. An example of that. What's that? What? Oh, yeah, see, I didn't go to that. So sorry. I know, my bad. But so if we take the complex plane and we use ds squared equals to 4, let's say, dx squared plus dy squared divided by 1 plus x squared plus y squared squared. This is sometimes known as a spherical metric. All right. So I won't bore you with the calculations, but let me just explain that if we're working so let's see here. Let me just do it in a different color. What is the story here? What's the curvature in each case? So the curvature, the big K, which is Gaussian curvature, the Gaussian curvature is 0. The Gaussian curvature is 0 for Euclidean space. The Gaussian curvature for the either the Poincare half plane or the Poincare disk, either one, I believe if I have my conventions correct, its curvature is -1. And if you set it for the unit sphere, I believe this gives you curvature 1. And so how does this work? So look at, this is, the Gauss's theorem right here. So do you see how this works? If the curvature is 0, and these are the angles, I should probably tell you. We're talking about a triangle with angles alpha, beta, gamma, okay? That kind of matters. You're like, what's alpha, beta, gamma? Kind of burying the lead here, aren't I? So if you have a triangle with alpha, beta, gamma, interior angles, Gauss proved that the integral of the curvature of that area, sum of the angles minus pi. Okay, so if the curvature is 0, the sum of the angles is equal to?
180.
Pi, right, 180, because that's just 0. But if your curvature is negative, what does it give you?
Negative pi. Depends on the area.
It depends on the area, right? So if like curvature is -1, you've got basically alpha plus beta plus gamma equal to what? Pi minus the integral of dA over the triangle. And if you've got k equals to 1, you've got the formula alpha plus beta plus gamma is pi plus the integral over the triangle dA. So what does this mean? This means that the sum of the angles in a triangle in a non-Euclidean geometry doesn't have to be 180 degrees. It could be less, it could be more. If it's less, you're in a hyperbolic geometry. If it's more, you're in a spherical geometry. Superbolic. Superbolic. That's not bad. I like that. I'm gonna give a technical definition for superbolic. I'm gonna work that into a paper. I'm gonna put a footnote dedicated to the one known as Shikamaru. There we go. All right. Anyway, so anyway, if I had my act together more, I would be showing you that actually all of these formulas are meaningfully interacting with all the complex analysis we did this semester. Like, for example, to get from the half plane to the Poincare disk, there is a Mobius transformation that goes from one to the other, and it meaningfully interacts with the metrics that I've written down, both of them. This spherical metric, it's nothing more than basically taking if we take the Riemann sphere, all right, and if you look at the geometry on the Riemann sphere as is induced, so like geometry you can define by restricting the metric on the larger space, like 3 dimensions. So if we take the notion of distance in 3 dimensions and we restrict it essentially to the sphere, that gives us a curved geometry on the sphere, all right? If you take that curved metric on the sphere and you pull it back to the plane under the Riemann, the stereographic projection, this is what happens. So these examples are connected to things we've done this semester. I don't have my act together today to tell you as well as I should. So therefore, it's not on the final, despite Ernesto's request. All right. So anyway, I just wanted to give you guys a quick look at it, because I think if I was to teach modern geometry, I would spend about maybe 2/3 of the course on the axiomatic stuff, and I'd spend at least the last third of the course on explicit formula models that exhibit the geometry on specific point sets, of which there are infinitely many. So anyway. By the way, there's so much more to say. Like, there's a whole theory of trigonometry on hyperbolic spaces that meaningfully involves like cosh and sinh and tanh. The hyperbolic geometry also is applications to like special relativity. The hyperbolic angle becomes rapidity, which measures like velocity transformations. They're analogs of this story. Essentially, there's just 3 kinds of geometry on a surface. There's either Euclidean geometries, hyperbolic geometry, or spherical geometry, depending on whether your curvature is 0, negative, or positive. And something interesting and similar happens in the story of relativity. You can either have Minkowski space, which is like the curvature 0, or you can have what's called de Sitter or anti-de Sitter space, which are analogs of like the spherical and hyperbolic geometry. But anyway, that's another course altogether, so let's stop there. Let me give you guys your test, and let's look at the solution. I don't have to. So Preston, does that suffice? Is that who is it I promised this to? I can't remember. Okay, so I did it. I can't say I did it well, but let's see here.
Although it would be nice to see where the equations come from.
Ah, yes. Like I said, that's like a whole other course. I mean, that curvature formula alone is mystical. What's interesting is that the Gaussian curvature is intrinsic to the surface. It doesn't depend on like how the surface is situated in the larger space. it's part of like that geometry that the Flatlanders could observe in their own, you know, little world.
I say you didn't see it.
Yeah. Well, I mean, I kind of know a little bit. It's talked about in other books that I've read. All right, well, eventually I will get to my email so we can look at the solution together. All right. Come on.
You're a troll. Literally every time you walk away from a test and you say that was the worst test I've ever taken, you get over on.
You said this is the worst test I've ever taken, and you apologized to Dr. Cook.
I'm gonna press the I jack.
Well, maybe you should learn the material better if you think it was bad.
I've only really had that experience once myself. There was a course I was going to drop,
And then you got like,
and I went to the professor. I'm like, I just don't understand anything. I'm going to have to drop your course. And he's like, oh, I'm sorry to hear that. Let me find your test. Let me look at your test. Let's look at your test before you make any decisions just yet. And I'm like, okay. And then he shows me the test. It's like 95 out of 100. And he's like, yeah, this is like the second highest score in the class. I'm like, what?
what class?
It was numerical methods
You.
with a,
I will not be taking this.
but I was at, but not it. Well, this was numerical methods in the computer science department at NC State with a professor named Funderlich, which is an amazing name, by the way. Funderlich.
Oh, I thought it was Thunder Blake.
Thunder. No. But he,
Are you going to edit this out of your recording?
oh no, it's fine. He, I must be careful not to name names. He liked that I knew how to like find equations of lines between points. You see, when all you do is typically teach computer science undergrads, hundreds of them, semester after semester after semester, and then randomly some idiot math physics major comes and takes your course because he has been poorly advised by an idiot advisor he never went back to that he should take that course so before he takes mechanics because it would be helpful. Nonsense. So I ended up taking this course without any of my friends. It was like just me. I'm a token math physics student here, and like I said, just computer science people. They just don't know math. So like I can, what's that?
I don't know what's more offensive, like computer science majors who don't like doing math, or math majors who don't like programming.
Oh well, the thing is, I thought I wouldn't have a good score in there because I didn't understand the programming at all. I mean,
You don't pay attention in class.
like I could write down the algorithm. Like I've always been okay with like, you know, writing a flow chart and saying this is the program like schematically. Fine, I can do that. Yeah. And but this is a silly place. All right. But anyway. Oh, the other thing that made me a formidable student in that class is I already had a class in assembly language.
Oh my god.
At my community college, I had a class in assembly language where we would sit and program Alexander, Mr. Anthony, Jack, and Preston, where you know I would sit and punch numbers into an 8086 board, make little lights go. And so the idea of like a register and a cache and flags, all that stuff, I already knew. So anyway, I really didn't learn much numerical methods from that class, though, hardly at all. And then my friends got to take a numerical methods class that was like much more about differential equations without me, and it was really annoying because I should have been in that class. All right, let's look at this together. Once you guys are ready. Oh, by the way, here's quiz 2. This should make you feel better, I think. By the way, I think there's signs of life for everybody. I mean, you guys missed some questions, obviously. But I think that there's hope if you just you kind of figure out what went wrong on the ones that went wrong and adjust accordingly. You'll do better on the final. And then I will replace this test score for some of you.
What's the quiz completion?
What's that?
What's the quiz completion?
Well, I did, yeah, pretty much. I checked to see if you... Is that, I feel like there's something under there. Whose is this? Ah, Jack. There you go. All right. Whew. Goodness. It's been a long semester. Let me assemble my pointy stick.
Do we get a page for the final?
Well, remember what you said yesterday?
What did I say yesterday?
You did say yes.
You said yes.
I said yes?
I remember that.
So Ernesto asked you.
Okay.
And you said a page front and back.
I do appreciate your mercy on this test.
Okay. All right, I guess you guys got a page of notes then, front and back. But if you're watching this in the future, that doesn't mean it's happening in your class. So shut up. All right. Just saying. So you guys did better than me. Like some of you proved the chain rule follows as a necessary consequence of the Cauchy-Riemann equations, and that's great if you did that. But if you didn't, I was also cool with it. But there's that one. Problem 2. I took 5 points off if you did the ratio test because I don't remember ever saying ratio test gives us uniform convergence. Did I say that? Or does it? If it does, you can come argue with me and get those 5 points back. Just saying. So you decide whether or not you can get those 5 points back.
It just says converge absolutely.
Yeah. I mean, of course it is, in this context, of course, it is absolutely convergent. Excuse me, it is uniformly convergent because it satisfies this Weierstrass M test. The question is, could you see that from the ratio test alone? I mean, I'm not 100% sure I'm right in taking off your 5 points. I'm not joking about that. You think about it. If I'm wrong about it, read the notes again, look into it, you know. Come back to me, I'll give you those points back. All right, so here, the Weierstrass M test, it is important that the M is independent of Z, so it's got to be based on, it can't be based on Z. So like 1 or 2 of you had an M that was based on Z, that won't work. Problem 3, the critical thing to notice here is that if we have a 0 of order 14, that means we got a formula like this, Z minus Z naught to the 14 times H of Z, right? And when we cube that thing, we get a Z minus Z naught to the 42nd with a cofactor which is holomorphic at the point and non-zero at the point, therefore it's a 0 of order 42. Now, I did give full credit for people who said a lot less than that, but I mean, there comes a point where I will take points off if you just write down 42, you know, even though it is the answer to many things.
You post this notes.
Will I post this? Yeah. I intend to. If I forget, let me know. So now this was a trap, and you guys fell into it, pretty much. So the point is, we've got -1 minus I is here. -1 plus I is here. The vertical line segment which connects them goes across the angle jump for the principal logarithm. So you cannot just use the principal logarithm. And if you write little logarithm, I just don't know what you're doing. Because little logarithm is like a multiply valued function. And okay, so fine. If the problem doesn't depend on the choice of branch, then it's a defensible notation. But here, it's all about the branch. So like writing little log is like, I don't know what to do with it. The other thing is some of you understandably tried to use properties of log. You know, like the log of a difference is the log of the quotient, but unfortunately that's just not the case in general. Like there's strings attached to that, and I think they get you here. So anyway, I use the log with the angle jump at 0 for this one because that way I don't have any trouble going from angle, 3 pi over 4 here to 5 pi over 4 down there. And I think I got minus pi over 2, pi I over 2. One of you got this, so. Does that make sense? So just, all right. That question essentially was where I tested the bag of tricks that you needed to understand for the analytic continuation. Like all of that work we did on analytic continuation was represented by that sole test question right there. Right, and that was pretty much it. This one here, by and large, you guys got this one. I was pleased, and you did it the lazy way, like me. For the most part, you guys used the complex argument, like these are the Cauchy-Riemann equations. But of course, in yesteryear, I might have looked at it in the real notation, or as my Benjamin sometimes says, yesternight. Yesternight. Oops. Anyway, so that's Cauchy's theorem. There are various things you could say here, but I think Morera and Goursat is probably best. Those showed us that complex differentiable implies continuously complex differentiable, and then because we have Cauchy's generalized integral formula, that links, that allows us then to take derivatives of arbitrary order, because the only thing that was keeping the generalized Cauchy-Riemann formula proof from being true for arbitrary complex differentiable functions was the assumption of continuity of the derivative. But once we have that from Goursat and Morera, then the Cauchy generalized integral theorem says, in fact, complex differentiable implies complex smooth, which is really special. That doesn't happen in the A calculus. In the A calculus, in the hypercomplex analysis that I work on, there is no generalized Cauchy integral formula. That's gone. That's special to hear. Okay, so this one, I think pretty much everybody got this, and I just took off points because it gives me joy, and I thought it would be funny. So, see, they're laughing. It was just a point, but there's no A sub n. What A sub n? There's no A sub n here. Anyway, I'm not that upset really, but So, and by the way, that's like one of my favorite points in this course is that proof of the fundamental theorem of calculus, fundamental theorem of algebra, is just so easy, right? It's really a very simple argument. It's so nice. Here, I was trying to make part A work out to 42 for shame. So it went sideways on me, obviously. But some of you had much less than 7 singularities in your calculation. There are 7. 1, 2, 3, 4, 5, 6, 7 of them. Because the cotangent is singular wherever you have division by 0. And that happens at any integer, because any integer gives you an integer multiple of pi in the sign. Which is a simple pole. And so since it's a simple pole, we can calculate by rule 3 that it has a residue of 1 over pi. Now some of you thought it had a residue of 1, which is understandable, so did I. I forgot there's a very important thing in that formula, which is what? Pi, right? There's a pi there. Or did they put a pi? No, there's a pi there. So yeah, anyway, that worked out to 84i, which some of you got. well, at least one of you got. There exists a student who got that. And then I think there also exists at least one student who got this as well. And I wasn't trying to make this a trap, but I understand why you fell into it. I probably would have too when I was taking this course, in terms of thinking that this is a triple pole, because, you know, by golly, it looks like a triple pole, right? There's division by z minus pi cubed, right? But the thing is, sine of 3 pi is 0, and that makes this actually, the numerator has actually got a 0 of multiplicity 2, a 0 of order 2 at pi. So you got order 2 over order 3. This is actually a simple pole, which is why some of your calculations were off base for that part. Some of I think 3 of you did that. I don't remember for sure, but anyway, it is actually a simple pole, and there are various ways of calculating that. I hypocritically have used L'Hopital's rule, and I've not even commented that's what I did, so shame on me. But I just found that to be, L'Hopital's rule does hold in complex analysis. It is a legitimate, I guess we had a homework problem, didn't we? I think I had one homework problem. We've had so many homework problems, I've forgotten, but this is actually a pretty good example of L'Hopital's rule. I differentiate once, and then what I did was I traded my 2 cosine for a sine 6z instead of the 3. Use the double angle formula or whatever it's called, and then I L'Hopital, and I get 9.
Wait, we didn't prove L'Hopital.
I told you I was being hypocritical.
Oh.
I admitted it.
So we can use L'Hopital?
Yeah.
But we've used L'Hopital.
I do think we proved a case of L'Hopital's rule in one homework problem that you didn't do.
But we didn't do.
Well, you don't remember it. No? It's funnier to me. That's all that really matters, right? The quality of a joke is inversely proportional to the size of its audience. So if no one gets it, it's a perfect joke. Oh, that one killed. Let's see here. So, no, I'm ruining it. Stop laughing. So I was going down this path, as some of you did, and then all of a sudden it hit me. I don't need to do that. Duh. Because we're trying to find the Laurent series centered at 0. So if I was trying to find the Laurent series centered at I or minus I, these would be super helpful, but I'm not, so they're not. But you can just straight calculate. So if the modulus of z is less than 1, we just apply the geometric series with a radius of minus z squared, which is true for within the unit disk. And we get the minus 1 to the n, which you guys like to drop for some reason. A lot of people just wrote parentheses minus 1 with no n up here. Like, what's up with that? Anyway, so and then z to the 2n minus 1 because there's a division by z. So there it is. Yay. And then the other one, the usual trick, factor the z squared out. And that gives us a 1 over z, which is nice because then that's radius, that's less than 1. Modulus of this is less than 1 for this situation outside the unit circle. And as such, I get this Laurent series. So it was just that. There are definitely harder versions of this question which could be on the final. I think you guys need to work on this one, generally speaking. Yeah? And this one also, this is not a hard problem, but a lot of people miss this.
Why are you so good?
I got a compass. So that's pretty much it. So the distance between z0 and the nearest singularity, we take the modulus of z0 minus I, which ends up being 1 plus I, which is square root of 2. I think at least 2 of you got this, maybe 3. Which is good. Now, this is definitely not holomorphic on the plane. Like this function has singularities at 0 and plus or minus I. That's what you got to watch out for. The theorem that you guys proved in quiz 2 was what? What was the theorem you proved in quiz 2? You proved for a function, it will have a circle of convergence that at least goes to the what? To the nearest singularity. Like it has to extend that far. We proved that in the quiz. Lots of signs of life here. I think with a little bit of work, you guys are well on your way to understanding this. Now, some of you have foolishly used the cross ratio. I'm going to get you on the final if you try to do that again. And I will simply add the instructions. Carefully simplify your formula if you'd like full credit. Because I'm not looking at that again. Like if I have to plug numbers into it to see if it's the right formula, it's not the right formula. Anyway, but I think you're right. You can hit them again. So, anyway, so listen, I tell you one's going to infinity, the other one's going to 0. That immediately says write down z plus 1 to get the 0 and z minus 5 to get the infinity. And that just leaves a multiplying factor out front, which if we plug in the other point, we work out has to be minus 1. So it's just that. And that picture is just to check that everything makes sense. I don't want to give you a problem which is nonsense. Technically, that's not part of the solution here. I mean, there are other problems where I maybe would let you be free to pick the points, but then my grading would suffer. By and large, people got this part B pretty right. Some of you got a 10 instead of a 20. I'm not sure how that happened, but sorry about that. It's not, it needs to be 20. When you put pi over 2 into this, what happens is the pi cancels and 20 over 2 gives you 10. 10 plus 10 is 20. And when you get minus pi over 2, you get 10 minus 10, which is 0. So that's how that all works. But it's two equations, two unknowns, which I guess is always dangerous, but there it is. And some of you didn't pick up on the method of the conformal mapping. Like this is a standard trick. You didn't know about it. Sorry about that. But the standard trick is this. We have, what we have done is we've solved it on the half plane, right? We have the psi on the half plane. We're trying to find a phi on the z plane. So the trick is just to let psi of f of z do what we need it to do, because the boundary of the circle maps to the boundary of the half plane in the same way as they're situated, which will put it gives you the boundary conditions you need. That's the whole idea here. And yeah, so this is the inelegant, well, I don't know if it's elegant maybe, the elegant formula that solves the Laplace equations as desired. And to see that that actually does work, I worked out, this is the bonus part. Only one of you did. And let's see here. So, it's kind of a pain. But after some calculation, I got 6y from over here because the xy and the minus yx cancel. Get 1 plus 5 is 6. And over here, this gives me an x squared minus 4x minus 5, which completing the square gives me x squared, x minus 2 squared minus 9. And of course, there's the minus y squared. So then the inverse, you do the inverse tangent of the imaginary component over the real component, the denominator cancels and you're just left with that. And I think that makes sense because if you look at that, when you're on the circle, the denominator is going to 0, which is making you go to infinity, which means you're attaining like the plus pi over 2, the minus pi over 2. And when that happens, well, when y is positive or negative, as you'd like. Like when y is positive, you got the, oh, goodness. What did I want? Oh, I've forgotten now. Maybe I might have a sign error actually. Huh. I'm not sure I believe this. I gotta think though. Oh, got to be careful. So If I'm inside the circle, that makes this negative. That's what I'm forgetting. So I've got